Hello. So, today we will talk on piezoresistive sensors. So, the last two sensors like pressure sensors we discussed is one is piezoelectric sensor and another is capacitive sensor, and now we are going to piezoresistive kind of sensing. Here I have put a picture of usual uh, kind of pressure sensor, okay, like a piezoresistive pressure sensor, and there you can see that this is the top side is the membrane, right. You can see the cavity here. So, below this top layer there is no material, or this is empty. So, this is like a membrane, and the pressure port is from here, right. You can see the pressure port from here. So, any gas which pressure we need to measure will come through this port, and then that will apply some amount of pressure on this membrane, which will then bulge. It will be like a paper, right. If you like a balloon, so it is like this. Let us say you have this kind of membrane, you can think this paper sheet as a membrane, and then it is clamped at all the edges. So, all the 4 edges it is clamped, and from bottom some pressure is coming from the whole membrane, right. So, accordingly it will bend or bulge. Now, we have put 4 different resistors which are not simple resistors, these are piezo resistors. What does it mean? Means it changes its resistance when it is under some kind of stress or strain. What is stress? Stress means that if you apply some force, then what is the force per unit area, that is the measure of stress, right. And then what is strain? Strain is like any amount of deflection per unit length or per unit area, like that, right. So, any kind of deflection from its original amount, that is strain. So, if this membrane is under stress, then it will bend or bulge, and then it will be under there will be a strain also, right. And these 4 resistors, so one is this, and then you can see half of this resistor and this resistor. So, this all these 4 resistors will be under the pressure or the stress, and because of that resistivity will change, okay. If we see the top view of the membrane, then the resistors are put like this. So, let us say this is the top view. Of the membrane, and then you have resistors like this, like this, like this, okay. So, let us say these are 4 resistors which are like R1, R2, R3, R4, let us say. Okay. Now, this arrangement and the placement of resistors are important, and how these are important, that will come in few slides, because the stresses at different region of membrane is different, okay. And also whether the resistor is under tensile stress or under compressive stress, accordingly its resistance change is also different, and also whether it is stress is across the axis of the resistor along the length of the resistor, or it is along the breadth of the resistor. According to that also resistance change varies. So, these things are important. Now, these resistors are connected like a Wheatstone bridge circuit. So, I hope that all of you have already know what is a Wheatstone bridge circuit, which is actually taught in 12th standard. So, in the Wheatstone bridge circuit you have 4 resistors connected like this. So, this is, let us say, one resistor, okay. So, these are the 4 resistors, and then we apply some amount of voltage, and measure the output voltage across these two junctions. So, let us say this is the input voltage and this is the V naught or output voltage. So, let us say now I put the resistance names, so R1, R2, R3, R4. So, let us put these resistances R1, R2, R3 and R4. Now, according to Houston-Bridge principle, if R1 by R2 is equals to R3 by R4, then the bridge is balanced. That means the voltage at this point and this point will be same. So, V0 will be 0. Okay, V0 will be 0. And from this Houston-Bridge circuit, if we apply the normal Kirchhoff's current law or voltage law, then we can show that according to, if we change any of the resistance, then accordingly the voltage, output voltage will change. So, for our pressure sensor circuit, what we will do, we will use the same Houston-Bridge, we will use the same Houston-Bridge, but we will use all the same resistors, all the resistance values are R now. Now, in this case the bridge is balanced, that means that the output voltage will be 0 because R by R equal to R by R, right. These resistances or the piezo resistors are placed in such a way that because of some kind of pressure or applied stress, both the opposite resistors will have same kind of change. Means that if this resistance increases by delta R, then so this is, let us say R1 and this is R4. So, if R1 increases by delta R, then R4 will also increase by delta R, okay, and R2 is increases by decreases by delta R, then R3 will also decrease by delta. So, this is has because of some kind of pressure, let us say because of some kind of pressure, its resistance has changed to delta R. So, then the other resistance, the opposite resistance of the bridge will also change by delta R. The other two resistance are designed such that these resistances will decrease by the same magnitude. That means resistance will decrease by minus by delta R, and this resistance will also decrease by delta R. And in this case, if we apply Kirchhoff's current law or voltage law from our basic electronics, then we can show that the output voltage V naught will be equal to V in into delta R by R. So, this R, what we are putting, the resistance of the piezo resistors we already know. This V naught is what we will measure, and V in is what we are applying, because this is the battery we have put in the circuit. So, we know how much is the V in. So, we know V in, we know R, we measure V naught, and then we can get the value of delta R, So, once we get the value of delta R, then delta R is related to the deflection of the membrane. So, we can back calculate the deflection of the membrane. Again, deflection of membrane is related to the applied pressure. So, then we can measure the pressure. So, what are the advantages of this circuit? Advantages will be like it is simple to fabricate. Then very minimal use of electronics. Very minimum need of electronics. linear characteristics. But one important disadvantage or limitation is temperature sensitivity. So, these circuits are simple to fabricate because we can actually make piezoresistor by doping the silicon membrane itself. So, that will come later, and then we need very minimal use of electronics because here the output voltage you can easily use, and then we can use some kind of simple amplifier to amplify the output signal, and accordingly we can measure. This is linear characteristics. Linear characteristics means you can see that the output voltage linearly varies with the change in resistance. So, that is also one advantage. And what another one limitation of this technique is temperature sensitivity. It means that whether the resistance of the piezoresistors or sensitivity towards towards the stress or strain is all these things are dependent on temperature. So, if we design the sensor for a particular temperature, it is difficult to keep the same characteristics for some very different temperatures also. Okay. So, this kind of temperature sensitivity is not appreciated. Now, we will show the stress distribution on the membrane. So, membrane is not a simple case like what we have studied in module 1 and 2 for cantilevers, etc., cantilever or simple beams. Then in that case we have actually calculated stresses at different points, right, and what is the deflection or what is the stiffness constant. But in case of membrane, stress is different and in different position of the membrane. So, as it is shown in this graph, that this axis is the distance shown in micrometer. So, let us say this is the membrane, this is the rectangular kind of membrane, and then you are like moving along this axis, right, moving along its width. So, this is center, there here somewhere will be the center, and then you are going to let us say 250 micron on this side and also 250 micron on the other side. Now, if we measure the stress at different point on this line, then you will get very different stress response. So, you will see that at the edges the stress will be high, and then as you move towards the center, stress start decreasing, and then after certain distance somewhere here it will go to the negative side. That means here it is tensile stress, where here it is compressive stress, right. So, here it is tensile stress and here it is compressive stress, and then compressive stress become maximum at the center of along this line at the center of the membrane. Then if you move towards the other side of the edge, then it again starts increasing, and somewhere it crosses 0, and then it will again have positive stress value. That means it is tensile stress. So, we are not derivation of this curve or the actual expression, derivation of the actual expression of pressure of for this curve is not part of this course, but you can actually intuitively understand this phenomena. It is like this. So, this is the membrane, and which is clamped at the edges, right, and the middle part or rest of the part is free to bend or move. Now, as it moves towards, let us say, upper side or lower side, whatever it is, now as it bends or moves, then this side as it is clamped, the stress will be maximum, because here only it is trying to pull the membrane. It is like balloon. So if you can consider it like a rubber membrane, like a balloon, you have pinned at the edges, and then you are applying some pressure from the bottom. Then what will happen, that at the edges where it is clamped, there will be maximum tensile stress, right, because it is trying to move away from that fixed junction. But that material, whatever is moving, that is trying to accumulate at the center, right, and then here it will be compressive stress. So as you move away from the fixed junction, the stress becomes smaller and smaller, and then you at the center you have more stress, more more compressive stress. And for the simple case, you can write this equation, that for a square membrane at any distance which is x from the center, let us say, which is x equal to plus minus a, the tensile stress will be P equal to a minus a by h whole square. So here a few thing we need to understand, that is, this is distance from the center. So let us say I am at a distance a, so I am at this point, okay, so this is my a. So at this point tensile stress or the longitudinal stress is P into a by h whole square, okay. So towards the center, so as you know that stress is a vector, right, so it has different direction. So let us draw the picture. So as you understand, for this membrane, if I take this membrane like this, okay, and then this is my center, let us say, and I am measuring the stress at this point. So this is the distance a from center. Now at this point the stress will be in all the directions, right. So it will be have a one component here in this direction as well as in this direction, and these two components are not same. This sigma L is the longitudinal component, and that it is saying that it is towards this direction, okay. And what is the transverse component? So that will come later, okay, but for this direction it is sigma L into sigma L is equal to P into a by h whole square. And also, as you can see, this is not a simple expression, and with changing the with changing the membrane dimension, it also changes, like it becomes, if it becomes from 500 cross 500 to 500 cross 1000, that means from square membrane to rectangular membrane, the stress characteristic with distance also changes. Now as I was showing, so this is the membrane, this is the the device or the pressure sensor, and then this part is which can freely vibrate or deflect. So this is the membrane, and then on top of that we have put these 4 resistors like R1, R2, R3 and R4. And fluid pressure is applied from the bottom, and then accordingly the membrane will deflect. And as we have seen in the last slide, that according to the pressure or according to the distance from the center, there will be, for the same pressure there will be different stresses, right, and then accordingly these resistances will change. Now as we put these resistors in such a way that R1 and R3 will have same kind of, so you see the position of R1 and R2, so these are like symmetric from the center, and the arrangement is also like that, it will have the same kind of deflection because it is under the same stress. So like here, for let us say this R1, if we draw the line, center is somewhere here. Now the radial direction for R1 and R3 both are this, right, radial direction is like towards the center. So this is like, this line is going through the center. So, center is somewhere here. Now, the arrangement is like that, that the stress towards the center is transverse for both R1 and R3. Okay, but this R1, this R2 and R4, for R2 and R4 if you see, then this stress which is towards the center, this is actually longitudinal stress for R2, but at this point this is actually transverse stress for R1. So, R2 and R4 are with the, so R2 and R4 are with the same kind of stress direction. Okay, so if the resistance changes, it will have the same sign. R2 and R4 both will be negative, let us say, and for R1 and R3 both will be positive and of the same magnitude, because it is from the same distance from the center. And as you have seen, the stress versus distance curve, it is also symmetric across the center. So, at a distance, let us say 50 micron from one side and 50 micron on the other side, have the same sign of the stress and also same magnitude. So, that is why the resistances are put like this. Now, this we have already told that then output voltage will be equivalent, will be equal to V in into delta R by R. Now, till now we have discussed that how placing on different region or different domain of the membrane have different kind of stress, and accordingly the resistances will also change. Now, how the resistance and the stress is dependent, resistance change and the stress is dependent. So, that we will discuss in the piezoresistive effect. So, what is piezoresistive effect? So, what happens is the stress or strain on crystal structure. So, whatever is your piezoresistive material, let us say it has some crystal structure, like it is usually single crystal silicon doped with some p type or n type material, and accordingly it has a crystal structure. So, strain on crystal structure changes its energy band structure. Because of this energy band structure change, we have change in the mobility. Mobility of carriers like electrons or holes, and that actually change resistance. That change resistance. Now, one important parameter in this context is gauge factor. Gauge factor. What is gauge factor? Gauge factor is measure of change in resistance with respect to the strain, right. So, what is the change in resistance? Change in resistance is delta R, but for different R value it is also different, right, because ultimately what we are interested in, that how much percentage of R is changed, right. If we are using 1 kilo ohm and if you are using 2 kilo ohm resistance, then both the cases delta R will be different. So, gauge factor is measured by what is the per unit change of resistance. So, that is delta by R for unit strain, that is epsilon. And what is epsilon? That we have already discussed before, right. Epsilon is equal to our strain strain, and that is delta L by L, where delta L is the original length of the resistor. Now from basic physics or electronics we know that R equal to rho L by A, where rho is the resistivity, L is the length of the resistor, and A is the area, cross sectional area of the resistor, right. Now let us assume this is a like a cylindrical resistor, or a like an wire, circular wire, and then so A will be something like pi d square by 4, like, or if d is the diameter of the wire and L is the length of the wire. Now what is the, how on each of these parameter actually R is dependent on each of these parameter. So for that what we need to do, we need to take first derivative of R with respect to all these parameters. So then we will get delta R equals to, so it will be like, let us say first we are taking with respect to L. So for that we can consider rho by A constant. So delta L plus, let us say with respect to rho, so in that case L by A we can take outside, and then this is delta rho and then with respect to 1 by A, with respect to A. So if we do derivative with respect to A, then we will get rho L will be constant, 1 by A will become minus 1 by A square into delta A. Now if we calculate, ultimately we need delta R by R. So if we calculate delta R by R, so that is we divide by rho L by A, then we will get delta L by L, rho by A will cancel out, delta L by A L plus delta rho by rho minus rho L by A, if we consider, then it will become minus delta A by A. And here now, so rho L by A will cancel out, so it will become delta A by A. Now A equal to, let us say pi d square by 4, where d is the diameter, right. So delta A will be pi by 4 into 2d into delta d. So delta A by A will be equal to 2 into delta d by d. Then we can write here that delta R by R equal to delta L by L plus delta rho by rho minus 2 delta D by D, where L is the length of the wire or the resistor, rho is the resistivity of the resistor, and D is the diameter of the resistor. One concept I suppose that you have already you already know, that is if we elongate any wire, like if I elongate this wire, let us say, then its length increases, right. So if the length increases, then the diameter have to decrease, because otherwise material will not be conserved, right, because you are not actually adding new material in that, or we are not changing the density, let us say, then in that case diameter will shrink accordingly. So what we see that the diameter will also decrease as we increase the length, right. So this is related by Poisson ratio, related by Poisson ratio. let us call it nu, and nu equal to minus of delta d by d divided by delta L by L. So, the ratio of change or the strain of in the diameter divided by strain in the length, and there will be a minus sign definitely, because if the length increases, if delta L is positive, then the diameter decreases, that is delta D is negative. So, there will be a negative sign. Now, so delta D by D can be written as minus of Poisson ratio into delta L by L equals to minus of Poisson ratio into epsilon, because delta L by L is epsilon, right. So, here we can write now delta R by R equals to delta L plus delta L by L, that is our epsilon, plus delta rho by rho, and then so it will be minus minus will become plus 2 nu epsilon, and gauge factor G equals to delta R by R into 1 by epsilon, right, delta R by R divided by epsilon. So, this will become as delta rho by rho epsilon plus 1 plus 2 nu. So, this epsilon is the strain that we can measure or we will know, nu is the material property that also we will know, and then delta rho by rho also we know. So, accordingly we can just measure the epsilon and can can calculate the gauge factor. This gauge factor is a measure of like how much is the will be the change in resistance per unit strain, okay, and depending on the material, this delta rho value like the resistivity value or the epsilon and the nu value, all these things changes, and accordingly gauge factor also changes. So, for like metal foil it is about 1 to 5, so gauge factor is not very high. Okay. Thin film metal, so there is a difference between metal foil and thin film metal, because metal foil here still the thickness will be like few hundred micron or so, whereas thin film metals can be even few nanometers. So, in that case the metal film has very low gauge factor, around 2. Diffuse semiconductor means let us say p type doped silicon or n type doped silicon, they have a high gauge factor of 80 to 200. And polycrystalline silicon means which silicon is deposited by CVD technique and or by some other technique, it is not single crystal silicon, rather it is a polycrystal silicon. In that case gauge factor is about 30. So, diffuse semiconductor, this is mostly used, or doped silicon is mostly used for even polycrystalline silicon is also used for making piezoresistive pressure sensors, because the high gauge factor. So, same amount of strain, if we use a doped semiconductor, then it will give a much higher amount change in the resistance, okay, or in the resistivity of the sensor, whereas if we use like thin film metal or metal foil, then it will be much lesser. So, this is the advantage of doped semiconductor, that the gauge factor is very high. However, there are some advantages of metal also, the metal films can be in case of metal film the signal to noise ratio is lesser, or metals have low resistivity. So, the amount of current will be higher, but we cannot use those advantages because the gauge factor, which is our prime requirement, that itself is pretty small for metal film. So, that is why we use doped semiconductor. Like in this picture we are showing p type implanted resistors. So, these resistors are p type doped. We have seen that gauge factor G is equals to delta R by R divided by epsilon. Okay. Now this epsilon is our strain. Now stress and strain is related by Young's modulus. And stress sigma is equal to Young's modulus. Let us say if it is, if we consider it y, then sigma by epsilon is equal to y, or Young's modulus. Now if we put that, then we can write that delta R by R is equal to G into epsilon is equals to G into sigma by y. So sigma by y, or Young's modulus, is our epsilon, right. So can be written as G by y and into epsilon into sigma. This G by y, this term, that is gauge factor by Young's modulus, this is called piezoresistive coefficient. Piezoresistive coefficient. And we can call it pi. So it can be written as pi sigma. So delta R by R can be written in terms of gauge factor and strain, as well as piezoresistive coefficient and stress. And for a piezoresistive element, we will know either the gauge factor or the piezoresistive coefficient, and accordingly we can calculate what should be the delta R by R if we can measure the epsilon and or the sigma, that is the stress.